Now we're hopefully good. And again, the measurement I just made there, the goalpost, that little delta y there, I'm going to call that 0.495. And from the top of the ball to the ceiling, that's, what did I say, 1.83-ish, something like that. I'm going to stick with the numbers I have. 1.84, I'm going to call this 0.51. All right. So I want to know those two numbers because then that's going to allow me to fill in some information on my VY VT graph. So VY VT, we're going to have the going up bit, which is 1.84, the going down bit, which is going to be negative 0.51, okay? And then since I know that this slope is going to be negative 9.81, I can figure out what is this time here. Because again, this is T. This side here is AT. So 1.84 equals 1/2 of AT times T, so AT squared. And I can solve that out for T. That's going to be 2 times 1.84 divided by 9.81. And somebody check that for me quick in a calculator. 3.6-ish divided by 9.1. .375. I did something weird there. Oh, yeah, there we go. Boop, this isn't T, this is T squared. You got yeah, it's 0.375 is the squared. Is that right? Okay, and so we take the square root of that. That gives us T, and that is 0.612. All right. So that's 0.612 seconds for the first part of the motion up to the peak. And then to get that velocity, I'm just going to take A, 9.81 times T, 0.612, and I'm going to get something in the ballpark of 6 meters per second for that. Okay? So now I can start to put my velocity triangle together because I know the actual launch velocity is 8.8. So if I know that the Vy is 6 meters per second, I know two sides of this right triangle that I'm struggling to draw here. Okay? So yeah, I can use a little sine theta equals opposite over hypotenuse, 6 meters per second divided by 8.8 meters per second. That gives me the sine of theta, and I get theta then to be right around 43 degrees. So a couple groups had that for the launch angle. That's good. And then I can use the trig to figure out the x velocity. Vx is going to be 8.8 meters per second times cos 43. And so that's going to be shaken out to be about 6.43 meters per second. So it should make sense. We're at an angle less than 45 degrees. We should have slightly more horizontal velocity than vertical. Okay? And now I can go in and make my Vx Vt graph, or at least start it. That's 6.43 meters per second. And that's just going to continue on as long as this thing is in the air. Okay? So how long is this thing in the air? Well, we got to go back to this thing. And again, I've got 0.51 for the area here. And let's just call this base T. And this is AT. So again, I'm going to have 0.51 equals 1/2 of, I'm playing kind of fast and loose with the signs because they're going to cancel out anyways. Half of 9.81 T squared. So 2 times times 0.51 over 9.8. That's t squared. So when I shake that out mathematically to get t, I get something in the ballpark of 0.323 seconds. So then the total time is going to be that 0.612 plus 0.323 seconds. I'm going to get 0.935 seconds. And now I come back down to my VXVT graph, and why aren't you erasing? There we go. This is 0.935 seconds. And so then I find this area, that's my range, 6.43 times 0.935. And I had the time screwed up initially. I was getting a value in the 8 meters, so I knew that was wrong. But this is going to shake out to be a little off on my numbers here. Let's see. 6.43 times 0.935, 6.01 something meters. Okay. And so that's all the fancier we have to get to sort this thing out. Okay. You can directly measure it. You know a change in vertical, whether it's the up change or the down change, you can just throw that on the graph and kind of sort it out from there. Okay. Didn't have to get anything too crazy going there. Really just needed a couple measurements in order to make that happen. So yeah, 6.01, that's about the farthest back we can get. And 5.98, which was period 6, I think. That was the farthest. They might have just been a little too conservative. They had 179.9 centimeters for the area of the initial triangle, 0.49 for the area of the final triangle. Because again, you want to make it go through. You want to be successful. So maybe not quite at the upper limit of what this is going to let you do. And their angle was like 42.5 degrees. All right. So that's that problem.